Test. Andrew, or is anybody on the live stream? Is sound coming through? And you have sound? Test. Sound. Alrighty then. Glare is a little bit higher than we want, but that's okay. Goodness gracious. So, turn the mic off. Good morning, everyone. Maybe not the best morning for everybody. The exam was too hard last night. I apologize for that. That's all on me. We're aiming for very high averages. The class is a straight scale, as you know. So if everybody gets an A, that's fine. Everybody could get an A. Absolutely, we don't have everybody getting C's, so or C's or below. But you also know the course points are different from the points you got on the exam. If you look at the syllabus already, the first exam is weighted less than the next two and the final. And this average was low. I hate to even say the number, but it was like 50-ish%. So what we'll end up doing, a couple things. I suspect the most straightforward and reassuring thing is this exam was going to be something like 20% of your grade. That'll probably drop down to like 5. So 15, 10, 5. So it was hard. It was conceptual. Usually I expect to get in a class of 150 and bright kids like you, I expect many people between 10 and 15 will get almost all of them right. They'll have perfect scores or just miss a couple. That didn't happen. So if you scored above 20, you're rocking. It sounds like you really know what's going on. That's great. And if you scored below 15, then don't worry, keep studying. Remember, it's still going to be conceptual as we go forward, not quite as rigorously conceptual. We have to balance the fact that we can't proctor you. So we have to have things that are creative enough that you can't Google them. But that went a little overboard. Sorry about that. Another thing I think we'll do is, I wish we could do this better, but last summer, the first exam went poorly too. And it was actually more calculational. So, but we did things in different order. I was going to say I could release the exams from last semester to you, last summer to you, um, but it's not super helpful because we're going in slightly different order. But that'll give you some more practice so you know what to expect. But as you know, also the homeworks, I'm just pulling from the exam database for about half of them anyway. And you probably recognized, you saw some things on the exam that were exactly from the homework, or I just, reversed the concept, or a little bit reversed the thing. So you had to think about it a second time. So don't panic. Don't give up on science and think you're not cut out for it. That some of you, it was your first exam, first college exam. The This will get easier to the extent that the exams aren't going to kick your butts. The material doesn't get easier, but the way I want you to tell me what you know on the exam. The I always write the exam to be a learning experience. It's part of the learning. It's the only time you have really thought about what's going on, is the day of the exam. Any other time you haven't prepared, and no one ever prepares to come here. So it's the time you really know what you want, and I want some of it to things to click in your mind, and you put stuff together on the exam. But we'll make that a less arduous experience on the second midterm. Also, why we have 3 midterms and a final. We give you a lot of chances to get points. Okay, so where were we? We were, when we last spoke, we did review last time. Just before that, we were talking about the difference between kinetics and thermodynamics and how they complement each other. So there's not a lot of kinetics as the formal material for this course. In fact, we don't even have a homework up for it, so I have to write one. But it'll be the things you want to know that are quite simple. We want to know the few things that we go through today, and you should be thinking about it as, how does kinetics and thermodynamics complement each other? What are the things that come together to make this curve this shape? We've looked at this curve a lot now. Here's water, hydrogen and oxygen, the elements going to water. This is the, if these are all in their standard states, liquid water, gaseous, oxygen, hydrogen, that is the enthalpy of formation of water. In this case, the free energy of the formation of water. And all of this, we said, is kinetics. Blah, blah, blah. All of this part, the difference in energies between products and reactants, is the thermodynamics part. And all this delta G tells us is what is favored at equilibrium. So the relationship between free energy and the equilibrium constant is something that we were trying to get you to explore on the exam. The free energy, when the free energy change is negative, when free energy is released, when you have work that the system can do, then that is the products are the favored state at equilibrium. We also call that spontaneous. I don't use that word as much. Favored at equilibrium is what we want to know. Spontaneous has other connotations that maybe make it confusing. So free energy is associated with the position of equilibrium. The greater the free energy, the more the products are favored, the greater negative the free energy. This part we haven't talked about, except briefly to say that you may not get from products to reactants. This reaction could sit at reactants, indefinitely, if this barrier is high enough. And this is the barrier we have to overcome. This is where we have to heat the reaction, put a flame on it, so that the particles in the surroundings start bombarding the particles in the system and give them the energy to either overcome potential energy between bonds, or bring them together in such a way that their collective kinetic energies of the reactants uh, allow them to switch bonds, going from this kind of bond to that kind of bond. So you should always think about it. The particles, even in a solution, they're moving around, and that's where their kinetic energy is. And that kinetic energy we can transfer from one system to another. The potential energy, we can't go from one system to another. We have to do it through the kinetic energy. And the particles have a huge range of kinetic energies. So we know that ideal gas, the temperature determines the energy, and it's all kinetic energy. So the temperature determines the kinetic energy, but they don't all have one you can calculate. The energy is 3/2 RT, but they don't all have that energy. They have a huge distribution of energies. Some are going ginormously fast, and some are nearly stopped in the great distribution. We're going to talk about that in detail when we talk about gases. But you should have in mind that reactions can kind of poke along slowly, maybe. When we talk about kinetics, we can start talking about slow versus fast. We can't talk about that at all for thermodynamics. So if you talk about slow versus fast, the sum of the particles in the reaction mixture have that high kinetic energy, and if they come together, some of them might have enough energy, collide with enough energy to get over this barrier. But the reaction pokes along because it's only a few of them that have that. So this is where kinetics and thermodynamics come together. We'll talk about this a little bit in just a little bit more detail, and we're going to move on from our discussion of energies. The activation energy is that amount of energy. You can compare it to how stable they are. When they are products, you had to get this much energy in the interim to get to those products. So you should already be thinking on the exam, I should be able to identify all these lines and places. I'm going to see figures on the exam, and I'm going to have to tell me something about the figure to show that you understand this bigger picture. So here we'll plot it again. This is the energy. This now is the actual rate of the reaction. This is how the concentration, so the concentration of X, say one of the reactants, changes over time. And we already know if X, it looks like in this case, X is a product, so we start out at low concentration of that, and it increases over time, and then the equilibrium stops changing, or the concentration stops changing. They get to equilibrium. They're still interchanging with each other, products and reactants. It's a dynamic equilibrium, but the concentration that you measure doesn't change, because whenever one goes to products, one goes back to reactants. So we've already seen this. We expect this to happen. This is the part where it's kinetic, it's dynamic, and this is the part that thermodynamics, the position of the equilibrium, determines. So kinetics takes hold first and gets you, driving you towards those equilibrium concentrations, and then thermodynamics says predicts that's where you're going to stop changing in concentration. So we can determine the equilibrium from the thermodynamics. So what affects the rate here? Initial concentrations, when I do this sub-zero here, concentration at 0 time, and we're going to plot time axes. We can do that for kinetics. We can't do that for thermodynamics. There's no time axis here. The factors that affect that, the initial concentration, I think that should make intuitive sense. If there are more reactants, then there are more collisions, because there's just more particles bumping into each other. So more of them, you're more likely, so it's a statistical argument, you're more likely that two will collide that have their collective kinetic energy gets them over that activation barrier. A catalyst, we know, can also affect that. And we're not going to talk in detail about catalysis, but it's one of the most important practical applications of chemistry in modern society. Catalysts make reactions go faster by lowering the activation barrier. And in your body, and many of you are going to be biologists or going to a biological science, in your body, these are the enzymes, the proteins that catalyze reaction. Virtually everything that happens in your body, every reaction, and you know there's billions of chemical reactions happening per second, and a huge variety of chemical reactions that are happening. The molecules that catalyze chemical reactions in your body are called enzymes, protein enzymes, and they do things that are fantastic. It's a beautiful area of science, but they're giant molecules, thousands and thousands molecular weight, and they're chains, and the chains fold up into these beautiful structures, and they fold up with brilliant little crevices and gaps where they literally take two reactant molecules and hold them next to each other so they can react. So they lower this activation barrier by saying, oh, you need to come together? I'll bring you together and hold you there till you react. So that's a beautiful area of science, and many of you in your next few chemistry and biology courses will study that in great detail. Enzymes do that in your body. We talked about this last time, the difference between kinetic and thermodynamic stability. So kinetically stable, you have a situation where the rate of the reaction allows you, this reaction goes fast, it gives you a lot of product to start with. This reaction is slow, it has a higher activation barrier. So as you go, it pokes along more slowly. Fewer molecules get over that barrier. But if you wait a long time, this one is the thermodynamically more stable. So if you're exchanging back and forth between all the products and reactants, when you form one of these, it's more likely to stay in this state. It gets down here, and it's thermodynamically more stable. So going backwards for it is there's a bigger kinetic barrier, a bigger activation barrier, and it stays down there, thermodynamically stable. These guys are going back, the yellows, compound, and then when they go forward again from reactants, they have another chance to make this more stable compound and get trapped in that lower energy well, that lower point on the landscape of free energy. Okay, we talked about this, so we understand what it is. Kinetically favored, lower activation barrier, thermodynamically favored, greater change in energy between products and reactants. So we could distinguish that. Distinguishing those two are the kind of questions you see on the exam. You know that now. If I have the choice of asking you to calculate a activation energy or a delta G, or identify them on the plot, it's likely I'll have you identify them on the plot. So let's look at more of these things that affect the reaction rate. Here's a very simple reaction, A going to B. We're saying that the rate of change of A, so this is the rate, how fast does the A concentration change over time? These two big deltas here mean what we have been using them for the whole time. The final minus initial value of A. How fast does A change for a given change in time? So this is the rate. A changes, it goes from 1 molar to half a molar in 1 second. That's half molar per second is the rate. So we can write that, it turns out, for some reactions, it's just linear with the concentration, the rate. And by linear with the concentration, there's a constant, m, x, and the plus b doesn't appear. It's a slope times a variable. The simplest possible straight line of slope kf. And we saw that as the reaction rate changed, that change in rate was a constant slope for quite a long time until it got right near equilibrium and it slowed down. So K we call the rate constant. You can write both the forward rate and the reverse rate of the reaction. We've already talked about that. If you're interchanging back and forth, that's what equilibrium is. The forward rate and the reverse rate become equal. So the reverse rate would be the B concentration, and you could, formally, these are initial concentrations, is how you determine the rate. You start from the initial concentration and get an initial slope. But it changes from initial to, in this case, if we're going backwards, B concentration decreasing to make A. But you can do it the same way. If the reverse reaction is linear in concentration, it's also written K reverse, the reverse rate constant. And you would expect that constant to be different because you know there's a different activation barrier going forward and reverse. So the ratio of those two things tells you how hard it is to get back and forth over that hill. We call rates that are just directly proportional to concentration first order. And I don't care if you know that. This is a first order linear differential equation. If this is the differential, for us, all we need to know is proportional to the concentration. I just put that up because you might see it. Or if you're good at math, change those into differentials and integrate them, solve the differential equation. At equilibrium, the forward and reverse rates are the same. That is what makes equilibrium. So now we see this beautiful marriage of kinetics and thermodynamics. Delta G tells us where you're going to end up. Kinetics tells you how fast you're going to get there. Initially, a very fast forward rate and a slow reverse rate, simply because the concentrations are low. As the concentrations get higher, this rate gets faster. That concentration gets lower. This rate gets slower until they balance. And that's the kinetic definition of equilibrium. Are they the same, or what's the relationship? They're both talking about equilibrium, so we should be able to get from one to the other. And indeed we can. If we set KRB equal to KFA, then the ratio of the rates, we want that to go to 1. The rate constants don't have to go to 1. The rates, that times the concentration has to go to 1. That ratio has to go to 1. But that ratio is the B concentration over the A concentration, which you can clearly rearrange. You set that rate equal to that rate, and this is the expression you get. And you go, excellent. Things depending on concentration. That's what equilibrium was. Rates depending on concentration. That's what kinetics is. And you see this beautiful thing. You should recognize this. This is Q. It's the concentration of the products over reactants. On the exam, I didn't go through the whole thing, but I just briefly looking through. Some people are giving Q too much significance, I think. Q is just any time. You look at what the concentration of the products and reactants are, and you plug it into this expression, that's Q. It changes. It can be any number. It can't be less than 0. It can't be negative. But it can be any positive number, any fraction, anything. And it does vary dramatically. So this is just, Q is just the ratio. It's just a dynamic running count. Can be any possible number. The amazing thing about nature is the ratio stops changing. And now we see why the ratio kind of stops changing. Those rates balance each other out. And we get to a situation where even though it's going back and forward, this ratio stays the same. And then it's a constant. It doesn't change anymore. So we call that the equilibrium constant. Q becomes a constant, and then we just give it a different symbol, K, so we can keep track. That is then at equilibrium, the equilibrium constant. So there's the beautiful connection between kinetics and thermodynamics, and it's all I want you to know about kinetics. We'll give you a little bit more information, though, about the relationship between the activation energy and this rate constant. The activation energy does determine the rate, but you don't see it in here yet. That information is in this rate constant. It's a catch-all rate constant that says all the factors affecting the rate are in here. One of them is concentration, because one of the things that can happen is more collisions, faster rate. But are the collisions successful? Do they have the collisions? What fraction of them have that high kinetic energy that gets the reaction over the activation barrier? That fraction is reflected, how many successful collisions you have are reflected in the rate constant. So I'm going to look at this in terms of this distribution of kinetic energies. So now I'm just looking at every reactant molecule. And what I just said a minute ago, there's these are kinetic energies. So I have a broad range of kinetic energies that the sample can have. This is the kinetic energy axis. So there's this many particles with that kinetic energy. And there's this many particles with that kinetic energy. The high kinetic energies, the higher you go, the fewer particles you'll have. But there's also particles that are moving incredibly slowly. Just a few of those, and just a few of those. And then the majority of the particles have this kind of average kinetic energy. So that's a plot you have seen before. It is just kind of an average. You take all the possible kinetic energies and you plot them out. It looks like the distribution of scores on an exam. We'd like those to look better. So since this is energies, we could put the activation energy on there somewhere. We could find, cast that in terms of a kinetic energy. Now, this is a little hand wavy, so this is hard to do in practice, but this gives you the conceptual idea. These particles, this bunch of particles here, those guys have energies above the activation energy. So those collisions are more likely to be successful. Of course, there's a broad range, a very high with a very low might have it. But this is gives you a conceptual idea of, oh, I see. Yes, there are high kinetic energies. There are some that have kinetic energy themselves greater than the activation energy. And that proportion would help you determine the rate. And this is for a relatively low temperature, this blue curve. relative. As the temperature increases, you might expect this to happen. That is, you get more particles with higher kinetic energy proportionally. I think you should expect that. We kind of understand energy goes up, but it's not maybe intuitively clear how exactly the distribution changes. We'll talk about this a lot more later, but this is how the distribution changes when you go to higher temperatures. So same number of particles, same area under the curve here. But now, activation energy, that doesn't change. So for the same reaction, many more particles with the higher activation, with the higher kinetic energy relative to the activation energy. So we can see why this temperature increase is causing the reaction to go faster, because more particles have the kinetic energy to get over that barrier, more successful collisions. So this says that K has to be a function of temperature, because K is the catch-all that determines your rate. The concentration doesn't change with temperature. That's the concentration. So it must be K that's changing with temperature to get the rate to change. And this is a complicated functional form. I'm not going to ask you to calculate a rate constant from an activation energy or vice versa on the exam. I just want you to realize, if you're clever and you can plot these things, there's information in there that tells you how the important thing we want to know, how does the rate constant vary with the activation energy? And it's not intuitive at all. It's that exponential function. We're not going to dwell on that. I'm just going to throw a few sketches up where there's a low activation energy and a high activation energy. So how does that affect K versus temperature? And really all I want to point out, which is the intuitive part, K is more sensitive to temperature. So as temperature changes, K changes more dramatically if the activation energy is high. So the ability to get over that barrier changes more dramatically with temperature. It has to do with the shapes of these curves and the available energy in the system. So the rate is sensitive to the activation energy when those activation energies are higher, sensitive with temperature. So that's the take-home lesson here, that the high activation energies makes K temperature sensitive. So maybe making that reverse reaction accelerate with temperature more than the forward reaction. So you get this idea we always have in any reaction. We have a difference between the activation energy going forward and reverse. That's the reverse activation energy. That's the forward activation energy. Actually, I think that's in the next slide anyway. So this one being more sensitive to temperature than that reaction rate. Okay, let's see if you're following. For the following reaction, the forward rate is much bigger than the reverse rate. So which is true for the equilibrium constant as temperature increases? Here's the chemical reaction, kind of a complicated one. Let's talk about this a little among ourselves. And if this is the case, you already have K forward much bigger than K reverse. And how does that affect this chemical reaction? So I'll start the quiz and you can talk about that amongst yourselves. Do I have information? There's some information you can look at. Oh, you can't look at that because there's a mistake on that one. Oh, but I'll give you this. to look at as you are talking among yourselves. Okay, let's come back together here, see what you're thinking. Press your button if you have not yet pressed it to get a vote registered. Speaking of getting votes registered, I will tell you the announcement went out yesterday. We will take the question from the exam that was least successful, had the least correct responses, and we'll present it to you tomorrow as a chem quiz. And you can vote on it and get the point back. Or if you got it right, you get an extra point on the exam. It's just an extra course point, scaled, of course, to the value of the point for that exam. But you get a chance to redo one and talk about it. We're not going to have you just vote. You'll be able to talk about it amongst yourselves and come to a conclusion. So about 100 of you here, equally split between increases and decreases. So we're not entirely sure here. Let's go through it together. So we have the forward and reverse reactions written there. Forward reaction, much faster than the reverse reaction. Lower activation barrier, higher activation barrier in the reverse. So these activation barriers go as the opposite of that. High activation barrier for the reverse, low activation barrier for the forward. And the reverse reaction is more sensitive to temperature because it has the higher activation energy. So we can see, if I look at this rate, this in the denominator is more sensitive to temperature. So we would expect the position of the equilibrium constant, to decrease as you increase the temperature. Does that make sense with everything else that we've talked about? So this is an exothermic chemical reaction. Heat is released. We're going to increase the temperature, which is kind of like adding heat. Not exactly, but more kinetic energy available to the particles. And yes, we expect Ks to decrease in that respect. So that all jives. Our Le Chatelier's principle, our hand wavy thing there, says decrease, favor reactants, go back towards reactants, however you want to think about it. And now our rate explanation brings us to the same result. So I think this is just going to summarize everything now. So we have for exothermic reactions, the reverse is more temperature sensitive. For endothermic reactions, the forward is more temperature sensitive. So we have the same ideas from our kinetics, how K varies with T, that we had in our thermodynamic discussion. So here's a catalyzed in both senses, and I can't emphasize enough, you'll see this all the time in, you'll have a question on an exam in your biochemistry or molecular biology class that says, adding a catalyst, does that change the thermodynamics? Does that change how stable or how much lower where the position of equilibrium is? No, the catalyst does not change this part of the picture, just the kinetic part of the picture. So the activation energy with the catalyst is smaller for both the forward and the reverse reaction. It changes the position of the equilibrium. It can't just change the forward rate, has to change the reverse rate, because the equality of the forward and reverse rate is what gets you to equilibrium. Unchanged are the thermodynamic parameters. Equilibrium constant is a thermodynamic parameter. And there was a question on the exam, and there were one or two questions that I was bummed that you didn't get, but it was too hard overall, so you're stressed and maybe you don't have enough time and you're frustrated. One of the questions was, what is K or delta G standard state for that reaction of AB2 going to the gaseous one, where you had the one gas AB breaking down into A and B. I asked for delta G standard, and I didn't give you any standard free energies of formation to get there. But delta G is minus RT ln K. The standard state delta G is minus RT ln K. We didn't give you the K either, but I gave you the concentrations at equilibrium. So you can calculate K, and that tells you the position of equilibrium. So does delta G standard tell you the position of equilibrium. Okay. So, and in fact, we did that in a calculation. I don't do many calculations, but we did that exact calculation for ammonia, the ammonia synthesis before the exam. Okay, which has the lowest activation energy? So we've seen this reaction, the hydrogen oxygen making water, and we know we can start that with a flame. Here it is. This is in the presence of platinum metal. We saw that reaction as well. That's where the platinum got really hot and we just blew a stream of hydrogen gas over it, reacted with oxygen in the atmosphere. Or this reaction here, which is H2O, H2 and O2 making H2O. So let's think about that. Talk about that as a group. I'll start this. So that'll give you that'll in your eye clicker will give you a screen capture, or just take a screen capture right now, and I'll give you those 3 possible explanations so you can think about it. Okay, so uh, here we are. Let's see what you're thinking. If you haven't yet, push your button and register your thoughts. Um, uh, Talk to each other in these Zoom breakout rooms. You're now all assigned to the same room. It's not going to change unless you ask. We can put you in a different room. But you're getting to know these people. Chat. That's part of the learning process here. Is talking amongst yourselves. I know that you don't know the right answer. I know these are challenging. So all you're supposed to say is, do you agree with any of those? Did anyone seem silly? All right, let's see what you're thinking. Uh, B, just overwhelmingly popular. So you're saying, the B's are saying, you keep telling me that all the catalyst does is lower the activation energy. That's just the definition. There's nothing mysterious here. Here you put a flame under it. Putting a flame under it makes it go faster, but that doesn't change the activation energy. It gives you more particles that have high energy, so it's going to go faster. The activation energy changing is the important part. You're getting in there and you're messing with the kinetics. Here, in none of these do you mess with the thermodynamics. And this is just the reaction here. So incredibly slow here. We know hydrogen and oxygen sit in that balloon forever. It, the equilibrium lies so far over here, the activation barrier is so high that hydrogen and oxygen are stable together in a balloon almost indefinitely. Give it that area, that activation energy, though, boy, oh boy, is this difference bigger. So that difference is huge. You get the big boom, but this is big too, which what keeps them at reactants. Oh, was that a different question? Is there another chem quiz here? Oh, which has the largest K? Let's just go through that one. So I'm sorry, I'll go back here. So now I'm going to ask you about the equilibrium constant. And goodness gracious, I hope you all get this right. Let's just vote on it quickly. So you told me which had the lowest activation energy, which has the largest kinetic energy, or sorry, equilibrium constant. Vote. You might not even have time to talk. Just gut feeling. I hope, I'm fingers crossed, that this is obvious. Somewhat tricky, but I think you see the trick, I hope. So go ahead, just take a stab. If you don't, let's get 60 votes or so we have a majority of you, and we'll just, it's totally anonymous. I can't tell what you're doing, so take a stab. A lot of you are saying, how do I do this? How do I even respond? Oh, that's a hint. How do you even respond to this one with your clicker? Okay, that's about 60 of you. Absolutely equal A, B, and C. That's how we respond to this one. Yes, for goodness sake, if you take nothing else home from Chem 1, take home the fact that a catalyst does not change the position of equilibrium. That is the position of equilibrium. K is K unless you change the temperature, putting a catalyst, going faster. Yeah, so either none have the largest or they all have the largest is the answer. And that's what you guys were saying. All of them have the same K. Okay? We have, and these two have the same activation energy. Different rates. All of them, though, end up at the same position. Just tells you just the time. Time is not a thermodynamic variable. All right. So we are going to do a gear shift slightly. A gear shift in that I want to tell you something about the properties of waves. And that's going to seem like just a jarring shift. But we've talked about the energies of this matter a lot. So these overall thermodynamic energies, products and reactants, energies of bonds, essentially, potential energies, kinetic energies. Those are, in a sense, macroscopic. Of course, the molecules are incredibly small, but in the better term is, we haven't talked about it yet, so I didn't want to use it, is classical mechanics. The kinetic energy is 1/2 mv squared for the particles moving along. There's nothing fancy. There's no fancy math. You use the same equation for a baseball as you do for a gas particle for its kinetic energy. But as you get tiny, things start acting funny. And you probably already heard this before, and you know this. Matter starts acting like waves, and light, which is the other important feature of this of chemistry. Light is how we've determined every structure, all the structural stuff we know about molecules comes from how they interact with light, and light is a wave. So we're just going to take an interlude here where we remind ourselves, and a lot of this will be a reminder. If you've had some mathematics class, how do you what is a wave? How do you plot it mathematically? You won't do any plots of waves on the exam. You just need to recognize the mathematical form of a wave. So what is a wave? Here is a wave. A wave is and it can be an ocean wave. It can be a sound wave. It can be a light wave, a radio wave. It's a oscillating, regularly varying function. Okay. And waves are characterized by their wavelength, which I've written here at the top, the distance from one crest of the wave to the other crest of the wave, the top of the wave. There's also a trough, the lower part of the wave. The wavelength is also the distance between two troughs. So it's the difference between two peaks or two troughs. That's the wavelength. That's a characteristic of a wave. We're going to talk about that forever. Lambda, wavelengths. Waves can travel with a given speed. I have here given s, so this whole thing can travel, and you're used to seeing that on the ocean, the wave, the peak of the wave coming at you. If you're a surfer, you're psyched. That peak is coming at me. I'm going to get on that peak and ride it because it moves through the ocean. So they can move at a certain speed. There's one other property, the frequency. The frequency is the one that is sometimes confusing to you, but it's frequency, don't get confused. It literally is how frequently, if I'm standing right here, how frequently does a wave pass me? They're moving, so I can get one wave passing me per second, 10 waves passing me per second. That would be a higher speed or a higher frequency. So you can see these things are related. How fast they pass you, how fast a wave passes you, if it has a short wavelength, then a lot of crests are going to pass you per second. Or if it's going fast, a lot of crests will pass you per second. So the speed, the wavelength, and the frequency are all related in waves. A way to imagine a wave being formed is if I have a little vector here spinning around a circle, and I just take and plot the y component for every place this guy is. So you can kind of draw it here in red. That's the y component when the vector is spinning here. If you let it spin, keep spinning over to here, then the y component is smaller. And then when it gets over to here, the y component went to 0. And then if it keeps spinning over here, the y component gets negative. So you go up to a peak, through 0, down to a valley, up to a peak. And here I've just plotted the values of that angle in radians. So that might be foreign to you, so just review it a little bit. It's not an important part of the course, but I do want you to kind of know that this angle, let me bring my little drawing thing here. When we start counting our angles from here, the positive x-axis, and then that angle theta changes. So that angle is 0 when you're along the x-axis, and the angle is 90 degrees when you're on the y-axis. It's 180 degrees over here. It's 270 degrees over here. And then 360 degrees is the same as 0. And that's why you're in a circle. That's why the system repeats. When you get back to one full circle, you're back to where you started, 0 y component. And here's just a chart that shows that. Here are the labels in terms of radians, in terms of pi. So 0 radians, pi over 2 is 90, pi itself 180, so pi units is 180, 3 pi over 2 down here at 270, and 2 pi, you've come back to the end. And I do that because we're going to plug those values into this functional form. So we're not going to plug the degree values into this functional form. And here I'm sure you probably recognize this. I think most of you have had some math. Y equals the sine, y of x is the sine function of x. Sine functions are this classic oscillating function. Cosine is the classic oscillating function. So these are wave functions. And we're going to talk about them a lot. That's a wave function. If you are going to plot and get specific, the wave function we've drawn here has the specific characteristics we've talked about. It has the wavelength is in there. So the wavelength tells you something about the functional form, and indeed it's in there. Oh, amplitude, I didn't tell you amplitude. Amplitude is the height of the wave, how tall it is. Surfers want the big amplitude wave. So those are in this functional form. So if you wanted to plot this out, y is x, it's a repeating function. It goes from 0 through 0, from 0, plus 1, 0, minus 1, 0, if the amplitude is 1. So it goes up to a, down to 0, minus a, back to 0. That's this sine function, and I think a lot of you have seen that. So that means you could also put the speed and the frequency in there if you want, because the speed and the frequency are related to the wavelength. So you could rearrange this and shove that in there. So the wavelength encompasses all of the properties of the wave in that wave equation. Okay? So, oh, shoot, I didn't check if that works. See if that link is available to us. Yes, it is. So here's a little toy you can play with. This shows us these traveling waves. And what we'll do is put them on top of each other. And I just want one wave, so I'm just squeezing them together here. So here is a single wave and traveling. So that looks like the ocean. That looks like here, I'm standing here. I can literally count off the frequency. 1 wave, 2 waves, 3 waves, 4 waves. A little more than 1 per second is the frequency. I can increase the frequency, probably. Yes, the frequency there, that is here. If I take this slider, let me make them both the same. Oh, let me slide them both this way. You guys can play with this and get them overlapping again. There goes that wave, high speed. And notice now the frequency increases. So frequency and wavelength merged together. I got them out of phase there a little bit. Can I do this? Get them moving kind of slowly so I can drop them on top of each other again. if possible. What I'm doing here is equalizing the speed of the red and the blue wave. I'll separate them again. There's a red and a blue wave. You can see that little thing I was talking about here, if you want. So spinning and going around at a angular frequency, and that wave going. So if you imagine a piston, something going up and down, that with some frequency, the radiating Y component gives you a wave. Keep that in mind. The radiating Y component, if you plot that, that gives you a wave. Okay, you can add waves. So here are two waves, and I will add them perfectly. So I'm adding the red. I'm adding the red wave and the blue wave to get this bottom wave. And you can see, oh, of course, it has twice. This bottom one has twice the amplitude because they're adding perfectly. Twice the trough because I'm adding them perfectly. We call that in phase. They are going up and down at the same frequency, same speed. So I can add them. I can add them in different ways. Let's say if they weren't beautifully matched, let's say they were out of phase, so that whenever there was a peak in this one, it corresponded to a trough in this one. Peak, trough, peak, trough. The sum here is boring. It is a flat line. So waves can cancel each other out. Question? So this is hard to see. The brightness is all the way down. Okay, we won't spend a lot of time here if this is hard to see. The link is there for you. And I have this summarized in a slide that's coming up next anyway. We're getting this set up so that I can project just the screen to you, and then you'll be able to see this beautifully like we see it here. With the lights in the room, the glare is bad. And I can't imagine turning the brightness up helps. That probably makes it worse. Oh, what if I turn the contrast way up? That doesn't make a huge difference. Okay, we won't dwell on this because you can have the link. I think the link might show up in your notes on the slide notes, but we can publish that and you can play with it. It's kind of fun. Oh, all I want to do is go back to PowerPoint. So let's talk about that thing that we were just talking about, this whole adding and subtracting of waves. So here's my waveform. It has a wavelength that is, I don't even have a full, well, I have a full wavelength plotted there, but I didn't go all the way peak to peak. But I did go 0 to 0. So that's a wavelength. It has some frequency. It's not moving, so you can't see it. It has a speed. This isn't animated, so you can't see it, but you could imagine that. And I can write that functional form. This blue curve has some amplitude. It has some frequency. Now, I've just taken all those 2 pi over lambda and just collapsed them into a constant, just so I don't have to write that every time. But the general form is a constant, and we know that depends on lambda times x. So that's just a general wave function. You've probably plotted that in your algebra classes, or certainly your calculus classes if you've had one. Here's another one. Okay, a different amplitude maybe. I've drawn it pretty similar though. It could have a different wavelength or frequency. 2 waves. I can add them, the 2 functions together. And that's what we were just doing. Add the functional forms. And you can just do it pictorially. Here, I take 1 point on each curve. I add up every point on each curve. Here, there's a maximum where there's a minimum here. Those two add to give me 0. So that's what we saw, flatlining. That flatlining has a special name, and I'll use it a lot, destructive interference. So the waves interfere with each other in a destructive way. The waves cancel each other out. The wave is destroyed by this kind of out of phase, this one's going big while this one is going small interaction. But you could also do the opposite. You could do constructive interference, where they perfectly are aligned, so you get the amplitudes adding. So you get a bigger wave, a higher amplitude wave. In this case, the frequency and wavelengths didn't change, simply the amplitude added, because they were, the sum has the same frequency and wavelength because the two little guys had the same frequency and wavelength. They don't have to. You could add different frequencies and wavelengths. So if the waves are traveling and you have a low frequency, so the energy in the wave is being transferred to you over time. It's kind of the power, but we're gonna talk about it in terms of energy. It's how many hit you. The amount of energy I can give to you is how many waves hit you per second. So the energy is proportional to the frequency. So I can draw a low frequency and a high frequency. And you know they're inversely proportional, wavelength and frequency. So if I have a low frequency, small number, I have a frequency is low, few per second, meaning wavelength is long, inversely proportional. Wavelength short, high frequency. And we're going to make this kind of general hand wavy explanation. The amount of energy I can transfer to you depends on how many waves hit you. It depends on the frequency. We're going to call that kind of a brightness of the wave. We'll talk about it more. I shouldn't say that. Let's just call that the energy. We're gonna associate brightness with how tall the wave is, the amplitude. So here's amplitude. So that's an intensity of the wave. So if you have a lot of them hitting you per second and it's a high amplitude, that would correspond to a bright light or a lot of energy per second. You have the same frequency, but you have this high amplitude. High amplitude gives you high energy. And that should make some sense to you. If you have a wave traveling and it's high amplitude, that's going to transfer more energy to you. You only want to surf on the big surf days. You need that wave to transfer kinetic energy to you. So it's got to have a lot of energy to start with, a high amplitude. And we're going to make this general relationship. The intensity goes like the amplitude squared. So that makes all the peaks positive. If you square this function, there are no negatives when you square things, so everything would be up on top. But we're going to call the intensity proportional to, drawing this little squiggle thing, it goes like the amplitude squared. The energy per second goes as the frequency. And here we talked about the power. The amplitude, the intensity is the power per second. How many watts hit you per second is the intensity. Okay, we can continue adding waves, and we can add them. We said you could add them with similar frequencies, and then you got that constructive and destructive interference. You can add them with different frequencies or wavelengths. So here's a green and red and yellow plotted. This one even has a different amplitude. So you have a bunch of waves adding together here. And this is, here's even another one, adding 4 wave functions together. And this time it's a mess. It's all different wavelength speeds, energies, frequencies. So that looks like a mess. That one is hard to draw. So you got to go in at any given point, and you have to add. You have to go in at any given point, and you have to add all the amplitudes. So the amplitude of the green one, the amplitude of the blue one, the amplitude of the red one, the amplitude of the yellow one, all along every point, and see what that is. And that's going to be a crazy thing as you go on. But there's an interesting property of adding waves. If you add, the more you add together, so this ... plus out to n, when n becomes a large number, when you add lots of waves together, it turns out you can mimic. So here it is written in functional form. This is the sum. I take the sum of a lot of wave functions with different intensities and different wavelengths, and I add them up. What does that look like? What does this sum look like? Well, it can look like crazy stuff. But you can also, there's a theorem, the Fourier transform, and I guess I'm not going to show it to you now because the glare is so bad and it's not that useful. We'll figure out a way to show you in real time. But there's this theorem that says if you're clever with how you pick your waves, how you pick this combination, you can kind of draw out any arbitrary combination of peaks and valleys. So this is one combination of peaks and valleys. Here's another broader combination of peaks and valleys. If you pick these guys appropriately, you can arbitrarily make any repeating function. Okay, so here I've drawn a very narrow one. Here's a broad one with a flat top. So this is called the Fourier transform, Fourier theorem. If I add enough waves together, I can pretty much approximate any shape I want to. And you can go the reverse. If you say, take any shape, I can go backwards and figure out what frequencies were involved to make that shape. That's super important in spectroscopy if you go forward in chemistry. We're not going to belabor it here. I just want you to keep that in mind. Adding a bunch of waves together, you can do creative things. So I can make this mess. If I take the sum of them, that mess, I have something that looks kind of neat. So now let's talk about the most important kind of wave we're going to talk about. We've been talking about waves in general. Let's talk about what if these are electromagnetic waves. So let's go back to this idea we had at the beginning of class. One of the first days we said, if you take a little charged particle, that kind of warps. It puts a dip in this space. It's not a real space. It's of charges. So charges have this fabric that I can distort. So if I put a plus charge there, the effect on a negative charge is they're attracted to each other. So this is going down a potential energy hill. And that looks just like going down a gravity hill, a real hill. So a negative charge at the top of a hill is like a ball at the top of a gravity hill. You push it, it'll roll down to the bottom. There's essentially a force pulling it down there, the force of gravity for the ball, the electromagnetic, the Coulombic, what we call it. You don't have to know any of those terms. All you have to know is pluses attract minuses. That's an attractive force. That's why closer together is lower on this energy scale. Okay, so if I plot energy, bringing them together, they go lower in energy. The way to remember that's kind of hard to remember. Could be counterintuitive. Think about it the other way. If they're close, how do I get them apart? They're close and they're attracted. In order to get them apart, I have to pull them. So that's putting energy into the system. So that's higher energy. The energy is coming from me to the system. The system gets it. So energy is conserved. That system is getting all the joules that I put in to pull them apart. So pulling them apart farther distance is higher energy. Okay? And in general, we draw it in general, you'll see us draw it a lot like this. Where the energy are all negative numbers. And we talked about that too. I put the 0 up here. The energies are all negative numbers. So that higher energy is a smaller negative number. It's higher in the elevation sense. Okay, so the plus charge down here, the minus charge up there, that separation is there, is the energy. This is a high energy situation. This is a low energy situation as that gets closer. So sometimes, in fact, all the time, we're going to put R0 at the high energy places. So our low energy places are downhill, negative downhill. Our high energies are lower negative numbers, smaller negative numbers. Okay. So, and you may have seen this happen. If you have static charges, you rub a balloon. We could have done this, should have brought a balloon. You can rub a balloon on your clothes. It picks up the electrons from your clothes. It gets a charge, and it will attract some positively charged things. So you can get it to attract or slightly positive charged things. You get it to attract a stream of water. You can get it to attract, say, a piece of paper. The paper comes close to that because there's that attractive force. Okay, positives, it's electrons attracting the positive nuclei of the stuff next door. And that is a very short range force. If the balloon's over here, you don't see that effect. The effect goes as the distance. So the size of the force drops off as R as well. So, but here's the weird thing about space. If I take charges, let's just go through it. If I take charges, here's a plus and a minus charge, a dipole. We'll talk about that more. There's an attractive force between those two guys. So this one wants to move towards that one, or vice versa. When they're close together, that's the high energy, the low energy state. So gone to low energy. What I'm doing is saying, let's flip this thing over, or let the charges come flying together and pass each other and go. So the negative one up here and the positive one down there. Now I have this this large force of attraction in the other direction. That we're calling that the high energy state and the low energy state. And of course, if I let them flip back together, then I'm back to low, and go back the other way, I get to high. And of course, there's all positions in between. So if you look at all positions in between, here are the different separations and the different directions of this force, because we're drawing the force from the positive to the negative in every case. That should start to look familiar to you. So oscillating charge starts to do if you look at the forces involved, the energy separation involved, the energy variation looks like this wave function. So, and you can actually do this. You can take little charge pairs, or let's just talk about one charge. You take one charge and you move it up and down. It affects charges at a distance. That is, that motion, plus, minus, plus, or up and down, up and down, up and down. If it's a positive charge, if they're close together, and I take this negative, positive, I move the positive, the negative is going to want to follow it because there's that force between them. But as you go far away, that is less because the force is small. But here's the wacky thing about space-time. If you get that frequency right, this oscillating dipole right, if it gets very high, that energy of going up and down, this oscillating energy, travels through space, empty space. And you can have your oscillating particle over here. And over here, this positive charge, this oscillating charge, here's another charged particle over here. This one operating at a high enough frequency, it'll make waves in this space that we've been talking about. We got that space where you got that trough. Those peaks and troughs, if you get that guy going fast enough, those peaks and troughs go through empty space. And they make this guy start to move. So this guy going, eventually this guy will start going. That energy travels through space. It's one of the weird phenomena of and you can think of it as a fabric, oscillating that fabric, and the waves going through and start to make something far away go. Get that frequency high, it travels, and it will affect action at a distance. So if you have these particles just sitting here and you're oscillating these, then they'll make the ones far away oscillate if you get the high enough frequency. So this oscillating positive and negative, positive and negative, positive and negative moves through space. And it's called an electromagnetic wave. And you can think of it as waves on a medium. Can't see the medium. We don't know what it is. It doesn't affect us because we're not very highly charged, but it affects charges dramatically. So let's keep that in mind. This action at a distance. And we'll just keep in mind generally this whole idea of potential and kinetic energy, just like the gravitational potential and kinetic energy holds. When we talked about gravity and the particle and a ball rolling up and down that hill, we had high potential energy and then low potential energy, high potential energy, but the kinetic energy, the speed that the ball is traveling, gets high. And those things traded places. High potential energy, I come to a stop. Then I roll down the hill. I go very, very fast. Lots of kinetic energy. The fastest I'm going is down here at the minimum of potential energy. I exchanged all that potential for kinetic energy. Fast here, stopped here. Zero kinetic energy, but high. Lots of kinetic energy, but low. And then back the other way. That applies again to the position of your wave. High potential energies in the middle here, traveling very fast, high kinetic energies. Now, when you do this super high frequency thing and you get that wave to distort the ether of space, to travel through space, it travels at this ginormous speed, the speed of light. And that's the fastest speed we can attain in our as long as we don't distort our little fabric of space that the wave is moving on. We know that that space is being distorted by the expansion of the universe. So there's a lot of cool things that happen here, but we're not going to talk about any of them. But now we're going to take our waves, and from pretty much now on through the whole class, we're going to fix the speed of our waves at this speed, because electromagnetic waves are the ones we're interested in. Ocean waves you can go play with. Electromagnetic waves are the ones we're interested in. They're traveling at the speed of light. They come from this fact that you can oscillate things back and forth. They have a huge variety of wavelengths, but the wavelengths and frequencies are locked because they're waves. So I'll just end here with one little point, and we'll pick it up tomorrow. You can make these waves. You know, well, maybe you don't know. You can make them at home. You gotta buy some electronics. There used to be this store called Radio Shack where you could go and buy these electronics. But if you could build a little electronic oscillator, if you could build something that gets a charge moving back and forth by, say, rapidly changing that potential energy, so the charge moves up and down and up and down and up and down, that energy, if you get that frequency high enough, is going to create one of these electromagnetic waves, and it's going to go flying out at the speed of light. And you know that's happening. We as humans are doing that in a lot of ways. The most famous way that that we all are kind of aware of, I hope you're aware of, if I were to turn on a radio in this room, it would get reception, because somewhere at a radio tower they're doing that. They've got a oscillating charge just going up and down, and that is the wave they're creating is traveling through space, and our antenna here, which is metal, its electrons start moving up and down, and we can detect the frequency that they broadcast at our radio, at our metal antenna. Those electrons start moving at the frequency those electrons were moving. So it can be done. We can make it. There's a lot of kinds of electromagnetic radiation, and we'll talk about that next time. Thanks for joining us this morning. Sorry again, the exam was too difficult. It wasn't you, more like me. Isn't that what you say when you break up? It's not you, it's me. But we're not breaking up. We're staying together. Don't worry about the actual score on this exam. We're going to scale it back so it doesn't impact the whole course, and we're going to bring everybody together, shooting for everybody gets A's, of course. That's the dream. That's the limit. Probably won't get there, but we don't want this average where everybody's getting C's and D's. That's just horrible. Okay. Take care. We'll see you next time.